Hello guys, welcome back to another video. Today we'll be looking at chemistry, in which we'll be looking at the rate and extent of chemical change. So our first topic we'll be talking about is the rate of reaction. So the rate of reaction is a measure of how quickly a reactant is used up or product is formed. So the collision theory helps understand rate of reaction. So for a chemical reaction to happen, reactant particles must collide with each other. The particles must have enough energy for them to react. The minimum amount of energy particles need to react is called the activation energy. And a collision that produces a reaction is called a successful collision. And also the activation energy is different for each reaction depending on how intense the reactions are. So there are different ways to determine the rate of reaction. The method chosen usually depends on the reactants and products involved and how easy it is to measure changes in them. So our key term is that activation energy, the minimum energy particles must have to react. So the rate of reaction depends on the frequency of successful collisions. So the mean of rate of reaction. The mean rate of reaction can be calculated using either of the two equations. Mean rate of reaction equals quantity of reactant used divided by time taken, or the quantity of product formed divided by time taken. So, and the things that affect the mean rate of reaction is measuring mass and measuring volume. So the change in mass of a reactant or product can be followed during a reaction. This method is useful when carbon dioxide is a product, which leaves the reaction container. And the units for rate are usually grams per second or grams per minute. Measuring the volume. The change in volume of a reactant or product can be followed during a reaction. This method is useful when a gas leaves the reaction container. The volume of a gas is measured using a gas syringe or an upside-down burette. Graphs. The rate of reaction can be analyzed by plotting a graph of mass or volume of product form against time. The graph shows this for two reactions. So on the left here are some graphs. So the first one, we can see different concentrations of hydrochloric acid. So we can see its volume over time. And so the first one is 2 moles of hydrochloric acid in the first, and the second one is 1 mole. And we can see the difference in volume given off over a certain time. The graph of total mass of product against time from start of reaction. A line labeled fast reaction rises sharply from 0 before gradually leveling off. A line labeled slow reaction rises less sharply but eventually levels off at the same height as the fast reaction line. The steeper the line, the greater the rate of reaction. Faster reactions are where the line becomes horizontal, finishes sooner than slow reactions. Also, the gradient of the line is equal to the rate of reaction. The steeper the line, the greater the rate of reaction. Faster reactions. When the line becomes horizontal, it finishes slower than slow reactions. So that's a key point to remember about faster reactions. That's why I repeated it twice, because it's a key point. Also, the rate of chemical reaction can also be measured in moles S-1. So that's higher tier. So guys, now we'll be looking at curve graphs. So the rates of 2 or more reaction can be compared using a graph of mass or volume of products formed against time. Usually it's volume, but mass is used sometimes. The graph shows this for 2 reactions. So to calculate the gradient for curved, we can't use typical way to calculate the gradient, which is change in x and y. So we have to use tangents to find the gradient of curve graphs. So what they do is they follow the curve at the beginning of the reaction, and the steeper the tangent, the faster the reaction. And then we can use it at different points to see how the reaction is progressing. So at the top, if it levels out, if the tangent is straight, we can see that the reaction is finished. And usually at the start, it speeds up, and then as a tangent gets less steeper, it shows that it's slowing down, and then the top, it's usually finished. So factors affecting rates of reaction. So four main factors affect the rates of reaction, and they are temperature, concentration, size, and the use of a catalyst. So temperature. If the temperature increases, the particles have more energy, so move quicker. Increasing the temperature increases the rate of reaction because the particles collide more often for more energy. And so the higher the temperature, the faster the rate of reaction will be. So next, it's concentration. So if a concentration of reactants is increased, that means there are more reactant particles moving around, and there'll be more collisions, so a higher rate of reaction. And size. By decreasing the size of a reactant, we are increasing its surface area. The greater the surface area, the higher chance of collision, so the faster rate of reaction. Finally, the use of a catalyst. A catalyst speeds up the rate of reaction, but it's not used up in the reaction. If a catalyst presents, the reactant particles can collide more successfully with less energy, and so the reaction can take place at a lower temperature. So finally, we'll be looking at reversible equations and dynamic equilibrium. Reversible equations. In some chemical reactions, the products of the reaction can react together to produce the original reactants. These reactions are called reversible reactions. So here's a typical example of this. Ammonium chloride. So ammonium chloride is a white solid. When it breaks down when it's heated, forming ammonia and hydrogen chloride. When these two gases are cool enough, they react together to form ammonium chloride again. So the reversible reaction, the way to show this is ammonium chloride, and there's two arrows showing the reversible reaction, and then ammonia plus hydrogen chloride. In other words, hydrochloric acid. So NH4Cl equals to NH3 plus HCl. The equilibrium position of a reversible reaction is a measure of the concentrations of the reacting substances at equilibrium. Guys, now we'll be looking at the final slide of this topic, which is about Le Chatelier's principle and equilibrium. The equilibrium position can be changed by changing the reaction conditions through changing the pressure, concentration, and temperature. When a reversible reaction occurs in an apparatus which prevents the escape of reactants and products, equilibrium is reached when the forward and reverse reactions occur exactly the same side. So if the equilibrium position lies somewhere in the middle, that means there's a similar amount of reactions and products. If the equilibrium position lies to the left, it means there are more reactants than products. And if the equilibrium position lies to the right, that means there are more products than reactants in the mixture of chemicals at equilibrium. When a change is made to the system at equilibrium, the position of equilibrium moves to counteract the change that was made. For example, if the temperature increases, the position of equilibrium moves in the endothermic direction to reduce the temperature, changing the pressure. If the pressure is increased in a reaction involving gases, the equilibrium position moves in the direction of the fewest molecules of gas to reduce the pressure. Finally, changing the temperature. In a reversible reaction, if the reaction is exothermic in one direction, it is endothermic in the other direction. If the temperature is increased, the equilibrium moves in the direction of the endothermic reaction. Also, another point to talk about is the effect of changing concentration. If the concentration of a chemical in an equilibrium is changed, the position of the equilibrium will move to the opposite, to oppose that change. If more of a chemical is added, the equilibrium position moves to remove it. If some of chemical is added, the equilibrium position moves to make more of it. So it's a similar concept when you're changing the pressure and temperature. So thank you for watching. I hope you enjoyed my video and look out for my other videos.